the chain rule. Let's consider taking the derivative of a function like f of x equals the square root of x squared plus 1. This is different than examples that we've done in the past. So you know that if we have a function y equals the square root of x, the derivative of this function can be shown to be 1 divided by 2 times the square root of x. And we know if we have the function y equals x squared plus 1, the derivative of this function is 2x. But I want you to notice that the function we have here is a combination of these two functions. In fact, this function is a composition of these two functions. And the way we get f of x here is by taking this function and plugging it into that function. And this is a composition. And to take a derivative of a composition requires a special technique called the chain rule. Let's review that technique now. The chain rule states if g is differentiable at x and f is differentiable at g of x, then the composite function capital F equals f composed with g, which is defined by capital F of x equals f of g of x, is also differentiable at x, and its derivative is given by the following formula. So the derivative of capital F of x is f prime of g of x times g prime of x. In Leibniz notation, we can write the derivative in the following way. If y is equal to a function of u, and u is equal to g of x, and both are differentiable, then dy dx is equal to the derivative of y with respect to u multiplied by the derivative of u with respect to x. To be completely honest, both of these notations can be a little bit confusing in the beginning. So I want you to think of the chain rule in a slightly different way. So if capital F of x is equal to f of g of x, I want you to think of g of x as being the inside function, and f is the outside function. And then when we go to take the derivative, we'll make reference to the words inside and outside. So the derivative f prime of x is, per the chain rule, f prime of g of x multiplied by g prime of x. And so f prime is the derivative of the outside function, but it is still evaluated at g of x, which was the inside function. And then we're going to multiply that by the derivative of the inside function. So the chain rule, if I want to put it more precisely, is the derivative of the outside function multiplied by the derivative of the inside function. Let's go back to our first example. So first of all, here I'm going to rewrite capital F of x to be x squared plus 1 quantity to the 1/2 power. So my inside function is kind of easy to identify. Normally, it is the function that is inside of the parentheses or inside of the radical. So the inside function here is x squared plus 1. And the outside function is going to be what we are doing to that inside function. So what we are doing is we're taking that function and raising it to the 1/2 power. So our outside function is the square root of x, or I could say x to the 1/2. Now to take the derivative, we are going to take the derivative of the outside function, but it's going to be evaluated at the inside function. So if I have to think of this as f of g of x, g of x is x squared plus 1, and f of x is the square root of x. And so the derivative, according to the chain rule, is f prime of g of x multiplied by g prime of x. So again, I am taking the derivative of the outside function, and that outside function is the square root of x, and we know the derivative of the square root of x is 1 over 2 divided by the square root of x. So that is our derivative, but then we're going to evaluate that at g of x. So f prime of g of x becomes 1 divided by 2 times the square root of x squared plus 1. So again, the x here is g of x. And then we need to multiply that by g prime of x. And if g of x is x squared plus 1, g prime of x is just 2x. And then if we do the math here, the 2's cancel out, and we end up getting x over the square root of x squared plus 1. Now I want to show you another way to think about this problem, because sometimes people get confused with this step right here. So here is another way to think about it. We have our function f of x is equal to x squared plus 1 quantity to the 1/2 power. So when I take my derivative, I'm going to start by taking the derivative of the outside function. The outside function is a power. So we are going to use the power rule, which says that we're going to bring down the 1/2 power. Whatever was inside the parentheses is now going to be raised to the negative 1/2 power. And this is because the power rule states that you have to subtract 1 from the power. But whatever was inside the parentheses before is still inside the parentheses. So this is the derivative of the outside function evaluated at the inside function. Then we have to multiply that by the derivative of the inside. So that is the derivative of x squared plus 1. And this is where we get 1/2 x squared plus 1 to the negative 1/2 multiplied by 2x. And then the 1/2 and the 2 will cancel out. And this becomes x over x squared plus 1 to the positive 1/2. And then we can rewrite that using square root notation. Let's take a look at these two problems. So first, we want to find the derivative of the function y equals the sine of x squared. And then we want to find the derivative of sine squared of x. So let's start with the first one. If y is equal to the sine of x squared, then our inside function is x squared, and our outside function is sine. So the chain rule says, when you take your derivative, you are first going to take the derivative of your outside function. Now, the derivative of sine of anything is cosine of the same thing. And then we have to multiply that by the derivative of that inside function. And so this becomes the cosine of x squared times the derivative of x squared, which is 2x. And then it's really important that you take this 2x and you place it in front of the cosine. Do not multiply these together. So this becomes 2x times the cosine of x squared. The second function is a little bit different. The second function is y equals sine squared of x. And remember, you can think of that as sine of x quantity squared. So notice that it's the same two functions as we had up here. We have a sine function and we have a square function. And here we have a sine function and a square function. But now the sine function is the inside function. And the square function is the outside function. So when I go to take the derivative here, dy dx is going to be start with the derivative of the outside function, which is a power. And to do that, we're going to bring the power down. Whatever's inside the parentheses stays inside the parentheses. And then we subtract 1 from that power. So again, this is just the power rule. And then we have to remember to multiply by the derivative of the inside function. And so this is going to be 2 times sine of x to the first power times the derivative of sine of x is cosine of x. And so when you look at these two derivatives, I want you to notice that they are very different. Even though we had the same two functions involved, it really matters which function is inside and which function is outside. Before we do this next example, I want to focus on a special case of the chain rule. And this is the case of the power rule combined with the chain rule. So if you are taking the derivative of some function raised to a numerical power, the power rule tells you that you take the power down, you subtract 1 from the power, you keep the inside function the same, and then the chain rule says you have to multiply by the derivative of the inside. Now, we've already applied this rule twice in previous examples, so let's apply it to this example here. So f of x is x to the 5th plus 3x squared minus x quantity to the 50th power. So the derivative, since I have a power outside, is going to involve bringing the 50 down in front of here, subtracting 1 from 50, which of course gives us 49, and then multiplying by the derivative of the inside. So we're going to have 50, and then the power gets reduced to 49. And what's very important is whatever you had in the parentheses stays in the parentheses. Do not change it. And then we're going to follow it up with the derivative of that inside function. And you don't necessarily have to write down this step in this way. I'm just explaining to you where I'm getting these things from. So we have this part, and then multiplied by the derivative of x to the 5th, which is 5x to the 4th, plus the derivative of 3x squared, which is 6x, and then minus the derivative of x is 1. And this is our derivative here. Another example involving the power rule along with the chain rule is to take the derivative of 1 over the cube root of x squared minus 1. So let's just observe that we can rewrite this as 1 over x squared minus 1 to the 1/3 power. And then I can move that power to the numerator if I make the power negative. So f of x is x squared minus 1 to the negative 1/3. Therefore, we can apply the power rule first, which tells us to bring the power down. So negative 1/3. Whatever was inside the parentheses stays inside the parentheses. And then we have to subtract 1 from that power. And then multiply by the derivative of the inside. And so this becomes negative 1/3 times x squared minus 1 to the negative 4/3 multiplied by the derivative of x squared minus 1 is 2x. And so now if I write everything in fraction form, we have negative 1/3 times 1 over x squared minus 1 to the positive 4/3 times 2x, which can be thought of as 2x over 1. And I can combine all these into a single fraction by multiplying all these numerators together, which gives us negative 2x. And then in the denominator, we have 3 times x squared minus 1 to the 4/3. Our next example is yet another example of applying the power rule and then the chain rule. So here, to take the derivative, we're going to have f prime of t is equal to 4 times 1 over 2t plus 1 to the third power. So that is the power rule. And then we're going to follow that up with the derivative with respect to t of 1 over 2t plus 1. Now, this derivative is a little bit more work. The way I'm going to do this derivative here is by using the chain rule. The quotient rule. And so this becomes, first part, multiplied by, the quotient rule says you take the bottom function, multiplied by the derivative of the top, derivative of 1 is 0, minus the top function, which is 1, multiplied by the derivative of the bottom function, the derivative of 2t plus 1 is 2, and then divided by the bottom function squared. And then if I simplify this, I'm going to have 2t plus 1 times 0 cancels out, so I have a negative 2 on top and 2t plus 1 squared in the bottom. And then here, if I cube the top, I get 1 cubed is 1. And if I cube the bottom, I get 2t plus 1 to the third power, and then multiplied by 4. And then we can combine all these into a single fraction. We have negative 8 on top, which is just 4 times 1 times negative 2. And now in the denominator, notice that we have 2t plus 1 to the third, and then 2t plus 1 to the second. And so if I combine those together, I get 2t plus 1 to the fifth power. Now, there is another way to do this problem, and I'd like to show you that method now. So what we could do in the beginning of this problem is we could rewrite it as 1 to the fourth over 2t plus 1 to the fourth. And 1 to the fourth is 1. And then we can rewrite this as 2t plus 1 to the negative 4. And now if I take the derivative f prime of t, we will apply the power rule. So we'll bring down the negative 4. And then we get 2t plus 1 to the negative 5, right? Because when you subtract 1 from negative 4, you get negative 5. And then we're going to multiply by the derivative of 2t plus 1. And so this is negative 4 over 2t plus 1 to the positive 5 multiplied by the derivative of 2t plus 1 is 2. And then when I multiply these together, I end up getting the same answer. And in my opinion, this is a little bit easier. So when you have a function, always be thinking about what you might be able to do to the function before you start taking the derivative, because sometimes it will make the derivative process a little bit simpler. In the next example, we have a combination of the product rule and the chain rule. So our function here, f of t, is t times the sine of pi t. So I'm emphasizing the fact that we have the product between these two functions. Now we also have a chain rule here because we have the sine and then the inside function is pi times t. But first we have to consider the product rule. So the product rule states that when you take the derivative of a product, you take the first function and you're going to multiply that by the derivative of the second function, and then plus the derivative of the first function multiplied by the second function. So that's the product rule. Now the chain rule comes in right here. So we have t multiplied by, what is the derivative of sine of pi t? Well, sine is your outside function, and the derivative of sine of anything is cosine of the same thing. But then we have to multiply that by the derivative with respect to t of pi t. Okay, that's the derivative of this part. And we'll come back and finish that. Then we have plus the derivative of t is just 1 times the sine of pi t. So what is the derivative of pi t? Sometimes people get confused on this, but I would just like to remind you that if I was to ask you what the derivative of 7t, you would have no problem just telling me that the derivative is 7. So pi t is just like 7t. Pi is a number. So the derivative of pi times t is just pi. So down here this becomes t times the cosine of pi t times the derivative of pi t, which is pi, and then plus sine of pi t. Now once you get your answer, it's very important that you write it in the correct format. This pi here should not be multiplied with the pi t, because this is the argument of cosine. So to help with this, it is sometimes useful to think of having parentheses there. And so we could have taken those, all the way up to the top like this. And then you're a little bit less likely to make the mistake of multiplying these together. So this pi needs to move to the front. So this becomes pi times t times the cosine of pi t, and then plus the sine of pi t. And this is our derivative. In the next example, we have a tangent function, but notice that it is tangent squared. And then we also have n times theta. So if I rewrite this, j of theta is equal to the tangent of n times theta quantity to the second power. So this is the first example where we have a composition of 3 functions. Our outside function is the square function. Our most inside function is n times theta. But then we have another inside function here in between those two. So when you use the chain rule, just start on the very outside and work your way inward. So j prime of theta, we're going to apply the power rule first. So we're going to bring the 2 down. When I bring the 2 down, whatever was inside the parentheses stays exactly the same. And we're going to subtract 1 from the power of 2, which gives us a first power. Then we are going to multiply by the derivative with respect to theta of tangent of n theta. And so this becomes 2 tangent of n theta. Okay, that is this part right here. And then we're going to multiply that by the derivative of tangent. Now, the derivative of tangent of anything is secant squared of that same thing. And then we have to follow that up with the derivative with respect to theta of n times theta. And so what we have here is 2 tangent of n theta times secant squared of n theta, and then multiplied by the derivative of n theta. Now, if you recall in our previous problem, the derivative of n theta with respect to theta should just be n. And so in the end here, I'm going to move this n to the front with the 2. And so this becomes 2n tangent of n theta times the secant squared of n theta. And it may seem complicated at first, but with practice, you will get better at this. In our next example, we have a little bit of a special case of the chain rule, and that is when you have e to a power that is another function. So anytime you have e to a function, the function up here is your inside function, and your outside function is your e function. So it's a little bit backwards from before. And again, I say it's because it's a special case. So when you have a function like e to the square root of x, what you're doing is you're plugging the square root of x into the e to the x function. So when I go to take the derivative here, we need to know the derivative of e to any power is e to that same power. So this is the derivative of the outside function. And then we have to multiply by the derivative with respect to x of the square root of x, because that is our inside function. So this becomes e to the square root of x multiplied by, and then the derivative of the square root of x is one of those functions that we should memorize, and it is 1 over 2 times the square root of x. And so in the end, we can write our final answer as e to the square root of x divided by 2 times the square root of x. And in our next example, we have a combination. We have the sum of two functions. In the first function, we have sine of 2x being plugged into the exponential function. And in the second function here, we have the exponential function, e to the 2x, being plugged into the sine function. So again, it's the whole process of knowing which is your inside function and which is your outside function. So when we take the derivative here, we're going to start with the derivative of e to the sine of 2x is e to the sine of 2x. Again, the derivative of e to the anything is going to be e to the anything. But then you have to multiply by the derivative of the anything. So here we have to multiply by the derivative of the sine of 2x. Then we have plus the derivative of sine of e to the 2x. So now our outside function is the sine function, and the derivative of sine of anything is the cosine of that thing. And then we need to multiply by the derivative of that thing. So now let's go ahead and compute these derivatives. So we have e to the sine of 2x times. Now what is the derivative of sine of 2x? Well, again, the derivative of sine of anything is cosine of that thing. But then now we have 2x. And so we have to multiply by the derivative of 2x. And in the second one here, we have e to the x inside of our cosine function, e to the 2x inside of our cosine function. And now we need to multiply by the derivative of e to the 2x. And again, the derivative of e to the anything is e to that thing times the derivative of that thing. So now, of course, these are the same, coincidentally, and the derivative of 2x we know is 2. So we have e to the sine of 2x times the cosine of 2x times 2 plus cosine of e to the 2x times e to the 2x times 2. And then the way I like to express these is by putting my constants to the front. So we're going to move the 2 to the front here, and I'm going to move this 2 to the front, and I'm also going to put my exponential function in front of my trig function. So this first part becomes 2e to the sine of 2x times the cosine of 2x, and the second part becomes 2e to the 2x times the cosine of e to the 2x. And again, I think it's a good habit to get into of putting parentheses around whatever you're taking the sine and cosine of, but it's not 100% necessary. So here is our derivative. And this concludes this lesson. Just kidding, this is not the end of the lesson. Let's do 2 more examples. Here I want to take the derivative of this very complicated function. Notice that we have a product, and then both of these are composition functions. So when I go to take the derivative, I need to first think of this as the product of these 2 functions, and therefore I need to use the product rule. And so the derivative dy dx here will be the first function multiplied by the derivative of the second function plus, and then we'll take the derivative of the first function multiplied by the second function. So now when I go to do the derivative here, I'm going to use the power rule and the chain rule, and the same thing when I take the derivative here. And so this becomes 2x plus 1 to the 5th power multiplied by, now this derivative involves bringing the power down, so we get 4, and then whatever was inside the parentheses does not change, subtract 1 from the power, and then multiply by the derivative of the inside. Plus, here when I take the derivative, again I'm going to use the power rule. So we get 5 times 2x plus 1 to the 4th, and then we have to multiply by the derivative of 2x plus 1. And then don't forget we still have this as well. So now let's go ahead and finish this up. We have 2x plus 1 to the 5th power multiplied by 4. I'm going to put that in the front. And then we have x cubed minus x plus 1 to the 3rd multiplied by the derivative of this is 3x squared minus 1. Plus, here I have 5 times 2x plus 1 to the 4th. The derivative of 2x plus 1 is 2. I'm going to put that 2 in front here, and then multiplied by x cubed minus x plus 1 to the 4th power. Now, this 5 times 2 right here, we can rewrite that as 10. And this is an acceptable form of the answer. However, there is a little bit of factoring that we can do. So I want you to see that you have 2x plus 1 to the 5th power and 2x plus 1 to the 4th power. So we can factor out 2x plus 1 to the 4th power. And then here we have x cubed minus x plus 1 to the 3rd power, and here x cubed minus x plus 1 to the 4th power. So I can factor out x cubed minus x plus 1 to the 3rd power. Also, here I have a 4 and here I have a 10. Those have a common factor of 2 that I can pull out. And then we need to think about what do we have left when we take all these things out. So when I take 2 out of 4, I have a 2 left over. When I take out 4 factors of this, I'm going to have 1 left over here since I had 5 to begin with. So that's going to be 2x plus 1. And then this was factored completely out. And then don't forget we also had 3x squared minus 1. When you take a 2 out of 10, you get a 5 left over. When we pull 2x plus 1 to the 4th power out of 2x plus 1 to the 4th power, that's completely gone. And here we took out 3 factors of this, so we should have 1 left over here. Now what we can do is we can simplify the inside of those parentheses a little bit. So let's go ahead and see what we can do there. And the key here is just to go slow enough to make sure that you don't make any silly mistakes. So if I multiply this out, I'm going to get 6x cubed plus 3x squared minus 2x minus 1 and then don't forget you still have a 2 out there. And then we have 5 times x cubed minus 5 times x plus 5 times 1. And then I have to distribute here, and that is going to give us 12x cubed plus 6x squared minus 4x minus 2 plus 5x cubed minus 5x plus 5. And if we combine all the like terms there, we should have 17x cubed plus 6x squared minus 9x plus 3. And then all the things that we had that were factored out are still there as well. So the answer is the product of all of these things. There we go. That looks a little bit better. In this example, suppose the function f of x is the product of the function x cubed and some unknown function g of x squared. Let's also assume that g of 9 is negative 5 and g prime of 9 is positive 2. And in this problem, we want to find f prime of 3. So first of all, we need to find f prime first. When I say f prime, I mean f prime of x. So let's go ahead and find the derivative. So recognizing that our original function is the product of these two functions means that we can use the product rule to find the derivative. So the product rule is the first function x cubed times the derivative of the second function, which is g of x squared, plus, then we'll take the derivative of x cubed and multiply that by g of x squared. And so we have x cubed times the derivative of g of x squared is g prime of x squared, and then we have to multiply by the derivative of the inside, and the derivative of x squared is 2x. That's the chain rule. Plus, the derivative of x cubed is 3x squared, and that is multiplied by g of x squared. So now if we just simplify this by multiplying x cubed and 2x, we have 2x to the fourth, g prime of x squared, plus 3x squared, g of x squared. So this is our derivative f prime of x. Now we need to find f prime of 3. And so to do this, we simply need to replace the x with a 3. And so this becomes 2 times 3 to the fourth power times g prime of 3 squared plus 3 times 3 squared times g of 3 squared. And this is 2 times 81 times g prime of 9 plus 3 times 3 squared is 27 times g of 9. But in the beginning, they told us that g of 9 is 5 and g prime of 9 is 2. So we're going to plug those in. And when we do that, this becomes 2 times 81 times g prime of 9, which is 2, plus 27 times g of 9, which is negative 5. And this is 324 minus 135. And if we do the subtraction there, we get 189. The final consideration for this section is finding the derivative of an exponential function b to the x. So we already know the derivative of e to the x is x. But now we would like to know what is the derivative of b to the x when your base is not the special number e. So to do this, let's first remember that if we have a function y equals b to the x, we could rewrite this function as e to the natural log of b to the x. And this is a property of logarithms. And then from there, we can rewrite this as e to the x times the natural log of b. So what I'm doing here is I'm using the properties of logarithms, which allows me to bring this power down in front. So now if I want dy dx, I'm taking the derivative of e to a power. Please remember that the derivative of e to any power is e to that power, and then times the derivative of that power. Now, what is the derivative of x times the natural log of b? So here again, I remind you that natural log of b is just a number. So x times the natural log of b is just a constant multiple of x. And we know the derivative of a constant multiple of x is the constant multiple. So this becomes e to the x natural log of b multiplied by the natural log of b. And then we'll remember that e to the x natural log of b is the same as b to the x, and so we get b to the x times the natural log of b. So a couple of quick examples of this would be, suppose we have a function like 5 to the x. The derivative of 5 to the x is going to be 5 to the x multiplied by the natural log of 5. So it's pretty simple if you remember this formula. And for our second example, suppose we have a function like y equals 3 to the x squared. The derivative of 3 to the x squared is going to be 3 to the x squared, but then we have to multiply by the natural log of 3, and we have to multiply by the derivative of x squared. That's the chain rule. And so this becomes 2x natural log of 3 times 3 to the x squared. So just reminding you here, the derivative of x squared is 2x, and then I am moving that to the front. And this concludes this lesson.